Yeah, you want to
I
come
got
up?
so much.
Yeah, I didn't know if he was.
Yeah, no, yeah, he's up in my
And
office.
I lost it all the next day. Just preparing class. Well, I host class at 8 and I teach at 9, so not really. Preparing like before it is preparing back to work.
That's not fun.
That looks like sci-fi.
Yeah,
It's
yeah.
like you're drawing a station.
Star Trek.
Oh, also, I don't think I will manage to get somewhere this week, but I can speak next week.
Okay, that's.
I'll commit to that. Unless anyone's planning on like doing anything on that.
No.
Okay. And I will plan.
Do you guys email? Oh, that.
Oh,
Shouldn't talk. You'll find a way to get sense on that too.
I'm like, what all have I said? I revealed how unprepared I am.
Definitely watch the beginning of this video. Oh.
It's not anything, it's just a phone.
No, but it is, it's a, circumventing Morse function, take the trisection and remove the center. Right, remove the central. And then that's what that Morse function. It's how, it's my vision of how trisections are.
Any questions?
So it's the core surface.
It's part of maybe that's circumventing.
Any questions? All right. So I think what I wanted to do today to kind of wrap up what we've talked about with Hagar splittings, all these big theorems, is to kind of, I think I'll try to give a proof sketch of Hawkins' lemma, which will be almost a proof, and modulo some exercises, and then talk about how this can be used to, how this relates to like the Reidemeister-Singer theorem and Waldhausen's theorem. And then at the end, hopefully I'll talk a little bit about Hagar splittings of connect sums of S1 cross S2, since we ran into a little bit of trouble last time. So this will be a proof sketch of Hawkins. And I believe that this, at least the bones of this proof are due to Johansen in 1991. And I was reading this and following it from Jesse Johnson's notes, which Johnson and Johansson. Do I have a year for his notes? I don't remember what year his notes were. Okay. And so the statement of Hawkins' lemma, again, is, so just to remember the statement is that every Haggard splitting of a reducible manifold is reducible. And for a Haggard splitting to be reducible, that means we have an essential two-sphere that intersects the Haggard surface in a single curve. So that's what we want to show exists. Okay. All right, so let's get to business. Let's start off with a Haggard splitting. Surface sigma, and we'll let S inside Y be an essential two-sphere. Remember, that means that S is embedded, but it doesn't bound an embedded ball. So the first observation is that we can choose H beta to be an epsilon neighborhood of its spine. And so we can make H beta very skinny. And the reason we do this is because then we conclude that the intersection between S and H beta is just a collection of disks, of meridional disks. And by meridional disks, I mean essential disks in the handle body H beta. So the idea is we're going to push all of the complexity of S into the alpha handle body. Okay. So first, let's just observe that if D is actually an empty collection of disks, then S is embedded inside H alpha, but H alpha is reducible, is irreducible as a 3 manifold. Okay. Every sphere, embedded sphere in a handle body bounds a 3 ball. Okay. Maybe in the vein of Hatcher, I'll just say, why? Are you reading? Or sorry, not Hatcher. Rolfson. I was reading Rolfson the other day, and it's just talking about some stuff, and then it'll just make a claim, and then it'll just say, why? I don't know. It's not but anyway, why? Okay. So that's a contradiction. So what we have is that D is not empty, and this implies that okay. And so let's let P equal the intersection of H with H alpha, and so P is some planar properly embedded surface. And let's let L be the boundary of P, which is also the boundary of D. And this is a collection of essential loops, simple closed curves in sigma. And so what we're going to do is we're going to assume that the size of L, the number of curves of intersection with our sphere and the Haggard surface, is minimal among all essential two spheres of the form S considered up to isotopy. Okay, so among all essential spheres and among all isotopy classes, choose the one that minimizes the number of components of intersection in this way. Okay. All right, so the first lemma that we'll need that I'll just leave as an exercise is that if P is a properly embedded surface in a handle body, then either or one of the following is true. First possibility is that P is compressible. The second possibility is that P is boundary compressible. And the third possibility is that P is a union of disks and spheres. And now, did I tell you guys what compressible meant a while ago? Or if I did, maybe we haven't really been using it. So the main reason I want to leave this as a lemma is because I don't really want to get into detail about what compressible and boundary compressible mean. But essentially what it means is compressible means there's some essential curve on P that we can surge along to split P into simpler surfaces. Boundary compressible is a similar thing, except the disk we use to simplify it is half on P and half on the, so maybe I'll just draw some pictures of what this looks like. So this is P, a compressing curve might be something like this. It means we've got an essential curve on P and it bounds a disk in the handle body. And so that allows us to do a surgery. Or maybe it looks sort of like this. Maybe sigma looks like this. Some piece of sigma, and then we have some piece of P that sort of does this inside sigma. Something like that, right? This is P, and then so the boundary compression looks like we've got an arc on P that is parallel through a disk to an arc on sigma. Even though it's essential in P, it's sort of an inessential handle body. And so you can do a karate chop along this disk. The move we did to stabilize a bridge or to perturb a bridge trisection is sort of this karate chop that I described. It's sort of like a boundary compression. Okay. Okay, so this tells us that if we have this properly embedded surface P, which is planar, then we can, it's either compressible, boundary compressible, or a union of disks and spheres. In our case, since it's connected, it won't have any sphere components. Since it's connected and because it intersects the surface, it won't have any sphere components. So this lets us conclude that, this will let us conclude that P is a collection of disks, but we have to be a little bit careful about how we get them. So let's see that. So first, if P, so the first option is that P might be compressible. And if so, then we compress. Okay, we surge or P along this curve. This either just simplifies P by reducing its genus, or it might split P into two, or sorry, we have to be a little bit careful. Sorry, P is a sphere. Okay, so since, sorry, P is not a sphere. Since S is a sphere, this splits S into S prime and S double prime. It'll split it into two spheres. And at least one will be essential. At least one of these spheres will still be an essential sphere. If they were both inessential, then they would bound 3 balls. And the union of those 3 balls along this disk would be a 3-ball bounded by S, which can't happen. So either at least one of them will be essential. So we'll throw away one of them and keep one that's essential. Okay. And this will either lower the intersections with the surface, or maybe it won't. Maybe we just, or maybe it will actually, maybe it'll necessarily lower. Yeah, it'll necessarily lower the intersections with the surface. Okay, so by our assumption of minimality, we get a contradiction, and we can assume. So we'll assume P is incompressible. Does that kind of make sense? Okay. If P is boundary compressible, Choose arcs, choose boundary compressing arcs. Let's see, okay, maybe we'll choose A1, A2, all the way up to A. Okay, so what do I mean by this? Well, if there's a boundary compression, that means there's an essential arc in P that looks like this. So maybe that's A1. Okay, and we can do the boundary compression along A1. And if the surface is still boundary compressible, then we can find an A2 and we could do that and so on. So we choose sort of many boundary compressing arcs like this to get a system of essential arcs in our planar surface. And so then the next lemma that we need, which will again be an exercise, is that if A is a collection of properly embedded arcs in a planar surface P such that A sub I is essential in P minus all of the arcs except A sub I. And if P minus the collection of arcs is a collection of disks, then what we conclude is that the number of boundary components of P minus the arcs is less than the number of boundary components of P. Okay. So let's just back up, and this is just a simple thing to prove about arcs on surfaces. And this is an application of innermost disk, outermost arc arguments. So both of these are totally within your guys' wheelhouse. Why do we need this technical lemma? Well, we want to we're working with this complexity measure that is the intersection of the planar surface, the boundary components of the planar surface. And when we do this boundary compression, two things can happen. If the essential arc connected different components of P, then it would decrease. It would look like a banding of L on the surface. So it would, okay. Sorry, let me just back up and say it more universally. This boundary compression looks like a banding of L on the surface. It's where when we do this karate chop, it's like attaching a band along the shadow. That band can either decrease the number of components of L or increase the number of components of L. Because if you have if L looks like this on the surface and you band like that, you get one fewer. But if L looks like this on the surface and you band like that, you get one more. And it's this case where you get one more that would make things a little trickier since we're trying to minimize L. But what this lemma tells us is if we choose enough arcs, then we actually will. Basically, you have a planar surface. Let's see if we can get an example of this. You got some sort of planar surface like this. Maybe your first arc has endpoints on the same thing. And so when you compress along this, we would get 2 annuli. So we'd go from 3 boundary components to 4. That's a priori a problem. But when you extend this to a complete system that cuts it into disks, you see that the result will actually be, let me just make sure that, so you need one of these for each annulus. So then this result would be 2 disks, I think, which is fewer than the 3 boundary components we started with. So this is just sort of a trick with the surface topology saying, maybe one boundary compression increases the number of boundary components, but if we do enough of them, it decreases the number of boundary components. But if we do this, this would contradict the fact that we've minimized L. So now we assume that P is not boundary compressible, boundary incompressible. And so by that lemma, we have to have number 3. This implies that P is a collection of disks. Okay. So P is a collection of disks. And D, on the other side, is a collection of disks, which means the collections of disks are glued together. And so what we get is a bunch of spheres. But S is connected, so we have one sphere split into 2 disks. So this implies P, order of P is 1, which implies, exactly, which implies that P union D is a reducing sphere. Any questions about that? So this is sort of an abridged version of what Jesse Johnson does in his notes, which, like I said, I think is based on Johansson's sort of reimagining of Hawkins' lemma. And it's pretty straightforward, actually. So Hawkins' lemma ends up being, basically the most useful tool in this sort of 3-manifold topology, because you're always sort of looking for these spheres to cut along and stuff. But the proof is actually, it's not too bad. Okay. Any questions? Nothing? Is it clear, or was it too fast? Like with my pre-calculus students, I either have to assume that everything makes perfect sense, or they're so desperately lost that they don't even want to bother asking questions. See, you guys are on the other side now. I think it's okay, right? Like I said, if you want a little bit more detail, you can look in Jesse Johnson's notes. Otherwise, I wrote this out in the questions. Okay, so now what I'd like to talk a little bit about maybe is, maybe I'll just draw sort of a picture. So basically, let's see how this goes. So basically, I have 3 important results. Hawkins' lemma. Let's put this in a cloud over here. And then we have Waldhausen's theorem. And by the way, so what is Waldhausen's theorem? I mean, just the statement in S3 that equivalently that Haggard splittings of the same genus of S3 are isotopic, or every Haggard splitting of S3 with genus at least 1 is stabilized. And then the last result we have is the Reidemeister Singer theorem, which says that any 2 Haggard splittings for a fixed manifold have a common stabilization. Okay, so and then so maybe just for the, this was Hawken in 1968. Reidemeister Singer was Reidemeister and also Singer, and this was this in 1933? 1933. And Waldhausen's theorem, Waldhausen, and this was in 1968. Okay, so now what do I want to say? So the first thing I want to say is that Waldhausen, in his proof, used the Reidemeister-Singer theorem, but not Hawkins' lemma. Even though they were, I guess, contemporaneous. So this was the path used by Waldhausen, but it was observed. So it was observed. So remark is that sorry, how do I want to say this? Okay, so I think what I want to say is that there are modern proofs of Waldhausen's theorem that use Hawkins' lemma, but not Reidemeister Singer. So what does that mean for my struggling picture here? It means that we can prove Waldhausen's theorem using just Hawkins' lemma. And so the citations here are Charlotte Thompson. Hopefully I'm getting this right. These arrows. Let me know if I do arrows that don't make sense. Charlotte Thompson, 1994. This uses thin position. And then we have Rubinstein, Charlemagne in 1996. And this is where the notion of a Rubinstein-Charlemagne graphic was introduced. And sweep, you use these sweep outs associated with Hagar splittings and fancy technology like that. And also hiding in here, I guess I should also put in here, is this Casson-Gordon result from 1987, which says that a weakly reducible Hagar splitting is either Hagar splitting. Sorry, I'm gonna have to rewrite it. Switch to white. If Y has a weakly third time's the charm. If sigma is a weakly reducible Hagar splitting for a three-manifold Y, then
Surface?
yeah, oh yeah, good, yeah. What did I write? Don't make me try a fourth time. I wrote exactly that. Okay. Then either, so one of two things can happen. Either sigma is reducible, or the second possibility is that Y contains an essential surface. Okay. And I think I maybe defined essential surface a while ago. This is, well, it's a closed surface in the three-manifold that doesn't admit a compression. Another way to state it is that it's a surface that's embedded in the three-manifold in such a way that its fundamental group injects into the three-manifold. I think that's the definition I maybe gave back in the first week of class, and then never used after that. And what does weakly reducible mean? It means you've got this surface and you're this Hagar splitting, and somewhere in your surface, you can find a beta curve and an alpha curve that are disjoint. And so the idea here is that you can do this untelescoping operation where this is kind of saying we've attached this one handle, or this Morse critical point of index 1, and this Morse critical point of index 2, this 2 handle, but since they don't interact, we should be able to exchange their heights. And so the idea here is to do this maximally, and if you do this maximally, then some of the generic cross sections of your Morse function away from the critical points will either be essential surfaces, or I guess even an essential sphere, in which case Hawkins' lemma tells us that the splitting is reducible. So this board represents a lot of machinery that we won't talk about that kind of gives even souped up approaches to the study of Hagar splittings and three-manifold topology. But the point is that it allows us to have an arrow here, which is, I guess, is Charlemagne Thompson, and there's also Rubinstein's Charlemagne, that give new proofs of Waldhausen's theorem that don't use Reidemeister Singer. And then the upshot of this is that then we can prove Reidemeister Singer theorem using Hawkins' lemma and volatile data. So there's actually a proof that looks like this. Did I write down a citation for this? I didn't. It's Feng Chun Lei. I don't know the year because I didn't have time. So this was maybe the first place it was observed that these new approaches here could be used to actually give a very quick proof of the Rademacher synchrotron. So I sketched one in the notes if you want to look at it. Actually, I didn't sketch it very much, but it's also in Johnson's notes. So the point is I guess why am I doing all of this? Well, the point is I kind of wanted to understand where is the real meat in these big sort of three-manifold Hagar splitting theorems. And I think from a modern perspective, the big meat, and even in I guess modern perspective, the big meat is in Waldhausen's theorem, which uses some sort of mature version of Hagar theory, thin position of Rubinstein, Charlemagne graphics, and stuff like that. The Casson-Gordon result. But Rademacher Singer then is not very difficult once you have that. Okay. Any questions about them? I kind of just wanted to sketch the logical elements somewhat. Okay. Okay, let's talk about this. So all right, so this issue came up last time, which was what can we say about Haggard splittings of connect sums of S1 cross S2? So a symmetric Haggard splitting, so let's say that sigma H1 H2 is symmetric if every disk, if every curve that bounds in H1 every curve, let's say on sigma, bounds in H1, bounds in H2 as well. So what does that mean? Well, it essentially means that the diagram looks like this. We get a curve here, we get a curve here, we get a curve here. Our alpha handle body looks like that. Well, what does our beta handle body have to look like? Well, it has to look like this. And so in particular, this implies that H1 union H2 is this manifold that I'll call YK, which is the connect sum of K copies of S1 cross S2.
So it has to be like slightly diffeomorphic to that.
Yeah, the diagrams are slightly more, yeah. Or even said differently, the Haggard split. So let me say this. So one interpretation. So there's this issue with Waldhausen's paper where he has a one-line comment about these symmetric Haggard splittings, and I think for a while people sort of interpreted this as a proof that Haggard splittings of these manifolds, minimal genus Haggard splittings of manifolds, are unique up to isotopy. But maybe one interpretation of what Waldhausen was actually saying, and maybe I should say that, where am I getting this account from? There's a paper of Saul Schleitner. So I also don't have a citation for that. I didn't write that down. There's a paper of Saul Schleitner, and his interpretation is that is that any minimal genus Hagar splitting of y sub k is symmetric. And his comment is that this should be a simple consequence of Hawkins' lemma, which in fact it is, because you take your minimal genus Hagar splitting in S1 cross S2, and you pick one of your, you pick an essential sphere. Well, by Hawkins' lemma, there's some curve on the surface that bounds, end up with, looks like this. Well, either way, you can sort of throw away just one chunk, or actually, if it separates off more genus, throw an even bigger chunk, and you can induct on the size of k. So one thing that this implies is that any two such splittings are diffeomorphic. Our volume till 2005, and it's remarking like that they're astounded that this hasn't appeared in before then. But this really does seem to be the first time where somebody has connected the dots to prove that any two, let's say, I'll put this in parentheses, symmetric Hagar splitings of y sub k are isotopic. And so maybe I'll just remark that the corollary, once you've established this, is that that y sub k has a unique Hagar splitting of genus G, Hagar splitting of genus G for each G greater than or equal to k. So this is what is commonly bandied around as Waldhausen's theorem, more general version of Waldhausen's theorem. That the statement for S3 also holds for these generalizations of S3. Of course, maybe I should make explicit. We usually treat y sub 0 as S3. The connexum of 0 copies of S1 cross S2 is S3. Okay, so I think I'll try to prove this. I think we have enough time here. Could have I added another arrow here? Not really. Okay. So let's let H1 union along sigma H2 and H1 prime union along sigma prime H2 prime be symmetric Hagar splittings of genus K or YK. And minimal genus, I guess symmetric implies the genus. Okay. So what we want to do is we want to build automorphism H from Y to Y. Maybe I'll just call it Y for now. H from Y to Y, such that H is isotopic to the identity, and such that H of, say, H1 equals H1. And from this, it would follow also that little h takes H2 to H2. Okay, so choose any automorphism. By automorphism, I mean like self-diffeomorphism or self-homeomorphism. Except that that's not what I want to write this. Any diffeomorphism F from H1 to H1 prime. So these are two handle bodies of the same genus, so they're diffeomorphic, so pick a diffeomorphism. And then observe that the double of F is an automorphism. And the double of F has the properties we want, is that it takes one Hager splitting to the other. Okay. So next we want to consider the induced map on pi1. So let's consider the induced map df star from pi1 of y to pi1 of y. And here we're thinking of pi1 of h1 as being identified with pi1 of y. And of course, it's the free group on K levels. Just a reminder. Okay. So, so a well-known fact about such maps on the free group is that there exists a topological or smooth realization of this map on the handle body. There exists a diffeomorphism G from H1 to H1 such that G induces the same map as DF, say DF inverse. So the citation that they give for this is, for example, Griffiths, 1962. I think the idea here is that H1 is just the neighborhood of a K pi 1 for a free group. So okay. So next we want to consider then the double of G from Y to Y. And we're going to let H equal the double of F composed with the double of G. So in particular, well, H goes from Y to Y, and H of H1 is H1 prime. Because H restricted to H1 is just F of G. G takes H1 to H1, and then F takes H1 to H1 prime. All right. So far, hopefully this is okay. So what's left to show? Right. So we wanted such an H that is isotopic to the identity, because if it's isotopic to the identity, then we can pull back sigma prime by an isotopy to sigma, or we can pull H1 prime by an isotopy to H1. That'll tell us. So if there's a map of if there's an automorphism isotopic to the identity, then the image of any object under that automorphism is isotopic to the thing that came from. Okay. All right, so let's see how this works. So let's let S be a complete system of spheres. A complete system of spheres for Y. And metric. Okay. So what we mean here is we mean as many essential, basically reducing spheres or Hawking spheres you could throw in such that the node 2 are parallel. I guess the intersection of these curves with sigma will actually enhance decomposition of the surface. So I guess we can stop real quickly.
Did you want G to go from H1 prime to H1? I'm just tracing through.
Oh, sorry, which one?
F went from H1 to H1.
No, this is a self-diffeomorphism, that's important.
Yeah.
Yeah, so, so the idea is that df is an automorphism of y, so it induces an automorphism of pi 1 of y. If we identify pi 1 of y with pi 1 of h1, then we can get an automorphism of h1 that is that acts the same way on that fundamental group as the automorphism of y. And then we can double it to write this composition of this. Maybe so. Oh, right. Well, we'll see. I guess I haven't said why that's key yet. But I mean, one thing we can observe is that, maybe I'll just put it here, is that what is H star? Well, H star is df star composed with dg, dg star, but dg star is just, on pi 1 is just g star, which is just df inverse. So this is the identity. It's the identity on the free group. So, pi 1 of y. So that was why we arranged it like this. We wanted to build a map that was the identity on pi 1, and so the map we were handed wasn't the identity. Okay. Of all of this is that since H star is the identity on pi 1 of y, what we conclude is that H is a composition of twists along the spheres. Okay. So because H is preserving the Haggard system, oh, sorry. Let me rewrite that. H is isotopic to a map prime from y to y. H prime is a composition of twists this sphere. The line automorphism of this manifold is to take the sphere determined by one of these curves, cut it out, and twist it in the curve. In other words, do a Dane twist on the surface at the curve and extend that Dane twist across disks into each handle body to get an automorphism of the ambient manifold. And now this, I didn't write this on this page of the notes, but this is where we need to invoke. This is where we need to invoke this key result by Loudbach. How much do we get that for? I don't know what year this was because I didn't write it down. But his key result is that any two spheres in a three manifold that are homotopic are actually isotopic. Okay. And so because this map is acting on an identity on pi 1, okay, and so up to homotopy, these spheres aren't moving, and so up to isotopy, you can assume that the spheres aren't moving, and we're just twisting along. And one thing we observe is that each such twist preserves H1, so H prime of H1 equals H1. Okay. Or sorry, so we want H prime. Okay, why do I not feel like we're done? Claim that we wanted to build a map as I'm not sure. Okay, thought a little bit at the end. The general line box map actually takes H1 to. I see. Well, the map, and then as I mentioned, the coordinates. Anyway. Okay, we'll try to fix it next time. So quickly. Compose H with this. I mean,